Welcome to EDU AMP. This is an A-level physics class all about waves. So what I want to go through today is I want you to know the definition of mechanical and electromagnetic waves. And then you've got to define the definition of longitudinal transverse waves. Should have met those at GCSE, but we'll go through those again. And then you need to define the following terms: displacement, amplitude, wavelength, time period, and frequency. And then you need to be able to use these two equations. Time period is 1 over frequency. I'm going to show you where the wave equation comes from, C equals F lambda. Then what's meant by polarization and unpolarized waves and plane polarized waves. And we'll look at the fact why only transverse waves can be polarized. Then we're going to describe what happens to light intensity if you basically rotate two polarized filters through 360 degrees. So, first of all is the difference between mechanical and electromagnetic waves. Well, mechanical waves, you know loads of them. You've got sound waves, which you're hearing now. You've got water waves, for example. And also you've got waves in a string. Now, the important part of all of these is they're all involving vibration of particles. In the case of sound waves, air particles are vibrating. Water, the water particles are vibrating. And string, well, the particles inside the string are starting to vibrate. The weird one, well, the different one, is electromagnetic waves. Now, to show you these, they come up like in this simulation shows you here. Now, electromagnetic waves simply come from their name. They involve two types of field, an electric field and a magnetic field. The electric field vibrates up and down, as you can see in red, in the vertical plane, and magnetic field vibrates horizontally, which can be shown in the blue. Now, they all do with varying fields, but the important thing to see is they are in perpendicular to each other. Now, main influence on you in a case of light, because light's electromagnetic wave, is the electric field. But these, what is meant by electromagnetic waves, is basically you've got electric field and magnetic field. Now, getting back to my slide going through here, good example then of electromagnetic waves is these come from the electromagnetic spectrum. So you have light waves, okay, you have microwaves, and you have X-rays. Now, all of these are different types of electromagnetic waves, and they have different wavelength and different frequency. So, define the difference between transverse and longitudinal waves. Well, longitudinal and transverse waves, again, you met in GCSE. Now, these are all about traveling waves. Therefore, you have like here a water wave where the wave is traveling along like this here. And a water wave is going along, and it's going from the left, going all the way to the right. Now, what I'm going to do is start showing you how a transfer wave is set up. So basically, if I pause this a second, you've got particles all the way along this red line here. And the particles vibrate up and down, but they vibrate up and down in a vertical direction. But the wave is going left to right. Hence, you see the blue ball, we'll start again, is going up vertically. And it's going up vertically here. But the important thing to realize is at no time do the particles vibrate in a horizontal plane going here. They only vibrate in a vertical plane. Because that one's there, this one's here, and they're all at different positions at a certain time, it then allows the wave to travel. And this wave is transferring energy from the left to the right-hand side. So therefore, we define a transverse wave is going to be a wave like a water wave where the particles vibrate perpendicular, which is this direction, to the direction of motion. Now, the second one, the tricky one, I think, is a longitudinal wave. Now, the longitudinal wave here, if you look very carefully at the blue ball, rather than vibrating vertically, you can see now it's vibrating horizontally. Therefore, the wave is still transferring energy from the left to the right-hand side, but now all the particles can only vibrate in a horizontal direction. Therefore, they are vibrating back and forth this way here. They at no time can they go all the way along the wave, but they are vibrating at different amplitude depending with time. And you may see here, where you can see a compression of the wave particles being put together, and here to see where they're being stretched out. And that's got a weird name, it's called refraction. And refraction means basically is where they'll be stretched out, and this is compression where they're going to be all stuck together. So therefore, we define a longitudinal wave is defined as where the particles vibrate in the same direction the wave travels. They vibrate horizontally, and also the wave is traveling horizontally from the left to the right. Now, getting back to my simulation again. So that basically is going to be your transverse and your longitudinal wave. Okay. Now, with that then, is you need to look at, that's the wave we've seen before when I got a transverse wave. You need to know what these terms mean. Now, looking at what those terms are, it's quite straightforward. The amplitude is what we say is going to be displacement from the equilibrium position. Now, the equilibrium position is this point just here, which is going to be the point of no disturbance. Therefore, this particle here has got a maximum displacement, and that maximum displacement is taken from the top of the wave or the crest of the wave to its equilibrium position here. Now that's going to be a maximum positive amplitude, and then we can say the one going down, that's going to be a maximum negative amplitude, and we normally use a symbol A for amplitude. Now the wavelength is the top of the wave or the crest of the wave to the crest of the wave. Use the Greek symbol lambda. Now, the important part in defining a wavelength is these 2 points must have the same displacement. Like you've seen already, that and that have both got maximum amplitude, therefore that's going to be the wavelength. You can also take it from a trough of a wave to the trough of the wave, because again, they still have your same displacement going down, but this one, both that's going to be minus A and that's going to be minus A. Now, so it's slightly different color. You also can have it from this point here to that point there. Again, that's going to be a wavelength. I think a lot of times easier to measure it from the top to the top. And displacement, ready to define it for you, that's how far any particle example here is above the equilibrium position at any time. Now the time period, that's the time a particle is going to take one complete cycle. Okay, and we give the symbol T, and it's obviously going to be measured in seconds. Now again, to show you that one, if I start the simulation again, it's basically a time that a particle takes to go from here to the top, going all the way down again, and going to here. In other words, the time for one complete cycle. But just make sure it has to go through a complete cycle. Then finally, frequency. Well, that simply is going to be your number. You can call it oscillations or cycle. I'm going to call it number of oscillations. And it's going to be basically number of oscillations is going to be in 1 second. It's got the units, Hertz, HZ, after the famous German scientist, and you might already met before, where you got KHZ, and that's going to be 1,000 Hertz, or we can say then 1 times 10 to the power 3 Hertz. And that's defining all those terms there. Now, next bit going through here is the wave equation. Now, the wave equation can be written 2 different ways. You know, V equals F multiply lambda. Now, what the V stand for, that is obviously going to be the velocity of the wave. F is then is going to be your frequency. And the one that we've met already, this one going here, that is going to be your wavelength, which is going to be lambda. Units of these, that's going to be meters per second. The frequency is going to be measured in hertz, and your wavelength is measured in meters. Now, you may have met the equation beforehand where you have CF lambda. Now, we use this a lot in electromagnetic waves because all electromagnetic waves travel at 3 times 10 to the power 8 meters per second. That's true in a vacuum. If electromagnetic waves do not travel through a vacuum, they can change speed, but through a vacuum, they all travel at the same speed. Now, where this equation comes from, if you can imagine a wave going along like this, traveling along, and this is where you got time is equal to 0 seconds, and then I can have t equals 1 second. Therefore, if you let the wave go past going that way, after time 1 second, the wave is traveled this far forward. Now, if you really think about it, isn't frequency the number of cycles per second? So if I had frequency was equal to 1 hertz, that would mean 1 wavelength in every second. Hence, if I had a frequency of 2 hertz, wouldn't then the wave travel 2 waves in 1 second? Therefore, if we now take a general term with them, with these, if you take time forward, depending whatever the frequency is, all I'm doing is multiplying the frequency by the wavelength. Hence, if I had 1 times lambda, I got 1 lambda. If it was 2 hertz, it was 2 times lambda. Therefore, if I've got any frequency called f, isn't the distance of travel going to be it's going to be f lambda. Now, you know the equation that velocity equals distance divided by time. Therefore, if your distance is going to be f lambda, I'm going to take the time as 1 second, because this time difference here is 1 second. Therefore, now the general equation comes down that v is equal to f lambda. And as I mentioned before, for electromagnetic waves, we use the symbol c, because they all travel at the same speed. Therefore, we've got c equals f lambda. That's where that equation comes from, and we use it a lot in work, first electric effect, etc. in year 12 in physics. Okay, now I'm going to explain what is meant by unpolarized, polarized, and plane polarized light. Now, remember the electromagnetic wave. You've got an electromagnetic wave going up and down. We have the electric field vibrating vertically, and perpendicular you can have magnetic field. Now, I'm only now going to deal with the electric field because that's the one that's a main influence in your eye when you pick up light waves. So therefore, just think about electric field at the moment. If you've got unpolarized light, we show it like this. What I mean by that is we can say the wave can vibrate in multiple directions. In other words, it can vibrate in a vertical plane going here, and then can vibrate in a horizontal plane this way and that way. Therefore, it can vibrate in any plane, and it keeps changing with time. We say it is unpolarized light, and that could be light from a bulb or a candle. Now, what you can hold polarizer, and a polarizer, what that does, it makes it only vibrate in a vertical plane. Now, to try and show you in a simulation with this, here I can have light which is coming along, and if a light comes along here, this is a polarizer. Now, it only allows it to vibrate in the vertical plane. So as the light goes through, it's now vibrating vertically, and therefore when it goes to this one, again vertically, and then what we say, this is going to be polarized light. Now, I can rotate and make it to be any direction I want to. I can then have this now in a vertical direction. Now, if this light already is polarized, i.e. going in the horizontal plane, this is only going to let light through in the vertical. So look what happens when the wave hits that Polaroid coming up here. Now, when it hits that Polaroid, it blocks it. It cannot get through. And the reason why it can't get through is because now it is basically only allow it in a vertical direction. Now, this one is vibrating up and down the vertical plane, therefore it's allowed to go through. This one again is going to be vertical plane and allowed to go through. These polarized, what they do is have ability to let light go through, but only in a certain direction. Now, in reality, where this can happen is in polarized, and I'll show you a little video clip here that explains it happening. Now, what you've got here is you've got polarides. Now, these polarides are basically, they've got a special material, celluloid crystalline structure in them. And what they do is they only let light go through at a certain polarization, i.e. vertical, horizontal. Hence, when light comes through on polarized, it takes some of the light out. Therefore, it makes it slightly darker. But what you can do is you can change the orientation of them. And I'll take that back a sec. Whereas, first of all, here, you've got these two that must be, for example, vertically polarized. Therefore, all the light goes through the first one, it's vertical, it goes through the second one underneath, also is vertical. Therefore, it appears to be like this. But as you start rotating them, this starts to happen. It gets darker and darker and darker and darker. So now you've got it completely black. Now, to show you that where it comes from is I can go back to my simulation here, and it's basically having this, where if I allow my simulation to run again, here we go. Here's light going to come through. Now this is going to basically polarize it in the vertical plane, so it will go through, it's no problem at all. But this is going to be horizontal, therefore it blocks it. So when it went completely black, that was what was happening. Okay, it didn't allow it to go through the second Polaroid. If I now take the second one and then put it in the same orientation as the first one, it goes through the vertical plane, going through here, and again it goes through that one then as well. Okay, so that's what's meant by basically polarized and unpolarized and plain polarized light. If it's unpolarized, very in different directions, this one is only going in a vertical direction. Now this is a question they love in examination. Why can a transverse wave only be polarized? Well, the reason why is you've got the longitudinal wave. Remember the transverse wave, the particles were vibrating in a vertical direction and the wave is going along here. But in a longitudinal wave, they were vibrating back and forth, but in the same direction as a wave. Well, what happens is if you're going to block anything out in longitudinal wave, you stop the wave going through what it can't travel from left and right. Only a transverse wave can be polarized because the particles vibrate in a different direction to the wave is traveling. Hence, well, in other words, perpendicular. When the waves travel in the same direction as the wave, well, you're going to block the wave completely. It can't happen. Therefore, you can't polarize longitudinal waves. Okay, so what I've been through is I've explained for you is all of these going through different types of waves, mechanical electromagnetic waves. I've told you the difference between longitudinal transverse waves. We defined all the terms: displacement, amplitude, wavelength, time period, and frequency. I've given you an equation for the time period, equation for the wave equation, what's meant by polarized, unpolarized waves, and plane polarized waves. And then what we've done is I quickly explained to you why only transverse waves can be polarized, and I've shown you a quick video shows you where you take two polarides and you rotate them through 360 degrees. Hope you enjoyed the video.